Last time, we have discussed an application of differential calculus wherein we make use the application of the rate of change. In this edition of Problem Solved, we're going to use another application of differential calculus in determining the maximum and the minimum point of a certain function. It can be useful in determining the maximum dimensions of a certain field, of a certain instrument, or a dimension of a certain material. Once again, this is Ian Erudite, and you're watching Problem Solved. So maximum and minimum value of a function or a line. Or in other words, or in some other books, it's called the optimization application. So what's that? So it's called optimization or maximum minimum value of a function since it determines the dimensions or the maximum value of a certain application. So suppose we have a line and we have here some certain conditions that we should bear in mind. So suppose we have here another function, it's described like this. So suppose the function looks like this. So something like that. But technically this is not a sine wave, but a polynomial function that curves like this. Okay. So we have there a certain point or a peak, where we call that as the maximum point. And we also have here the lowest point, which we call as the minimum point. And each point is determined by its critical values. Which then an ordered period is defined. Okay. So what are the things that we should bear in mind in solving optimization problems or this kind of application? Okay. The first thing that we should remember is that we should find the first derivative. And equate the first derivative and solve for the critical values. Second, find the second derivative. So that you'll know if the function is a minimum point or maximum point. And then third, substitute the critical values in the original equation. Okay. The original equation, that will be the given equation. You need to substitute that back there, so that you'll know the values of the ordered pairs. And then for the second derivative, so that you'll know if that is max or minimum. Okay. A max point is usually an inverted bowl. And for a minimum, that is a regular bowl. And if our second derivative, f double prime of x, is equals to 0, that means, or exactly equal to 0, and single point, so that would be our point of inflection. So, how do we determine if the point is max or min? Okay, so the point is maximum if, so if our f double prime of x, okay, so we substitute the value we obtain from the critical value of f sub x, or f prime of x, okay, as that, okay, the critical values. If the value of our f double prime of x is negative, then that means the point is maximum. If the point is positive, that means that is minimum. So those are the two conditions. So, okay, we have here sample problem. So, given f of x equals x squared minus 6x plus 5, determine the critical value or values if necessary and graph approximately. Okay. The first thing that we're going to do here is, okay, so we're going to find the first derivative of this function. Okay. So, that would be f of x is equals to x squared minus 6x plus 5. So that the first derivative f prime of x would then be equal to derivative of this. So that would be 2x minus derivative of 6x, so that would be 6. Okay, so that would be 2x minus 6, and this would be our first derivative. To determine the critical values, we need to equate this to 0, the first derivative into 0, so that 2x minus 6 is equal to 0. So that we can now solve for our critical value. So manipulating this equation, so we have 2x is equal to 6. So that x equals to 3, and that would be our first critical value. So how do we determine the other pair or the other half of this value? So we're going to substitute this value back to the original equation, which is f sub x. So that f sub 3 is equals to 3 squared minus 6 times 3 plus 5. So that this would be equal to 9 minus 18 plus 5, and that would be equal to 9 minus 18, so that's negative 9 plus 5, so that is negative 4. And that will give us one critical ordered pair, so that would be 3 and negative 4. Okay. So as we can see, this one is a parabola. Okay. Parabola opening upwards, and this is the vertex. So we know that for a parabola, okay, so the vertex would be either the maximum or the minimum point. Okay. So for this case, let's see if this value is for maximum or minimum. So how do you find that? So we're going to find the second derivative of the function. So that f double prime of x is equals to, okay, so what's the derivative of 2x? So that's simply 2, and the derivative of a constant 6 is equals to 0. So that f double x is equals to 2. Okay, what are our condition? So if the value is 2, okay, so as we can see, okay, so that would give us that the value is at minimum since this is positive. Okay, recalling the previous or what I've said later on, okay, or what I've said a while ago. So if f double prime is positive, that would be at minimum, and if f double prime is at negative, then that would be a maximum value. So that if we're going to approximate the graph of this function, it would look something like this. Okay. So we have a Cartesian plane. Okay. So point is 3 and negative 4. Okay. So x is 3, y is negative 4. So 1, 2, 3, somewhere here. 1, 2, 3, 4, somewhere here. So the parabola would be opening upwards like this. And that would be our approximate graph. And since this is positive and that's minimum, okay, we have here a regular bowl. Do you have any questions or problems with regards to this problem? So comment it out. Don't hesitate to send me a private message through my videos. So okay, we have here another sample problem. Okay. So given f of x is equal to 2x cubed minus 9x squared plus 12x minus 3. So determine the critical value or values if necessary and then graph approximately. Okay. So just like what we did with the previous example. Okay. So we're going to find the first derivative based on the original equation, which is this. So let's copy that. So f sub x is equals to 2x cubed minus 9x squared plus 12x minus 3. Okay. So that our first derivative f prime of x would then be equal to, so derivative of this, we bring down 3 and then solve this, so that would be 6x squared. Derivative of this, so that would be negative 18x, and then plus 12. Derivative of constant is simply 0, so we can simply neglect that. Okay. So we now have here a quadratic function. So this is a factorable trinomial. So we will have two critical values. So how do you solve for that? Okay, so we're going to equate that to 0. Okay. So right after we equate that to 0, we can solve for the roots. Okay. So that we have there two roots. We're calling the rules for this. If this is negative and this is positive, therefore we have two negatives there. Okay. So we can factor out 6, okay, so that would be 3x. This is 2x. Okay. And then, what will be the values for this? Okay, so let's try to crisscross. Okay. So we have here 3 and 2. Okay. So 3, 2, and then we have here we have here 3 and 4. Okay. Or rather, so 3 and 4, so that one. Okay, it's correct. So that's exact. So we're going to put 3 here, and we're going to put 4 here. So 3 times 4, okay, so it's a call. Okay, so we have 3, 4, we have here 3, 4, we have here 3, 2, okay. So 3 times 4, so that is 12. 3 times 2, so that is 6. And we can form 18 out of that, okay? So that's correct. So if we're going to utilize this, okay? So we now have properly factor this out, okay? Then let's equate that to 0, okay? Then we're going to have two critical values for this. We can divide this into 2, so we have here 3x is equals to 3. So that value of x is equal to 1. We don't know this yet if this is a maximum point or a minimum point. Let's set this aside. And then for this one, we have 2x transposing 4 to the other side. That's equal to 4. So that x is equal to 2. And as of now, we don't know if this is a maximum or a minimum value as of late. Okay. So let's now test, or let's now find the other half of this, or the other pair, or other part of these critical values. So how? We'll substitute both values to f of x, okay, to find our critical points. Okay. So if we have an ordered pair, that is called a critical point, by the way. So critical point. Okay, that's called a critical point. Okay. So let's solve for the critical points. So we have here 2 times 1 quantity cube, okay, minus 9 1 squared plus 12x minus 3, okay, and that would be our first critical value. So I've already solved that for primarily, so that will lead us to the value of 2, or you can use calculator to solve for that and verify that, okay. So that we have our first ordered pair, which is 1 and 2, okay. Let's determine later if that's the minimum point or the maximum point. Okay, let's try to solve the other equation, okay, or to solve the other critical point. So that would be at x is equal to 2, okay, so 2 quantity cubed minus 9 squared quantity squared, okay, 2 quantity squared plus 12, 2 minus 3, okay. So solving that would give us 1, okay. So try to calculator that, okay, or try to solve it later. And that will give us another critical point, which is at x is equals to 2, our y will be equal to 1. So we already have two critical points based on our two critical values. Okay, so let's now determine if these values are maximum or at minimum. Okay, so let's find the second derivative of f prime of x. So that f prime of x, which is the second derivative, okay, would then be equal to, so 6, 2, okay, so bring down 2, so that is 12x, minus, so 18x, okay, so that is simply 18, and then the derivative of a constant is simply 0. So we have here 12x minus 18, okay. So let's now test the values, okay, if that is a minimum or a maximum. So at x is equal to 1, let's substitute that here, okay. So we have here 12x is equals to 18. Okay. So we have here sorry for that. Okay. So substitute x equals to 1 as directly as that. Okay. So f double prime of x is equal to 12 minus 18, and that is equals to negative 6. We have here a negative value for 1. That means this value is at maximum. Okay. It's negative. Therefore, that is at maximum. So if we're substituting at x is equals to 2, okay. So 24 minus 18, so that will give us 6, okay, positive 6. And that would mean that the value is at minimum. Okay. Now, let's test if the value is, okay. So minimum at 2, okay, maximum at 6, okay, at 1, okay. So let's now, since we have two critical values, we also need to find the point of inflection. Okay, so to find the point of inflection, we're going to utilize the second derivative and equate that to 0. So that f prime of x would then be equal to 0, equal to 12x minus 18. Okay, so we have here 18 is equals to 12x. Okay, and that would give us, okay, x is equals to 3 halves. Okay. Substituting that back to the original equation to solve for our point in which the 2 points will meet. Okay, so let's try to solve that. I forgot to calculate it right away. Okay. So we have here 2 quantity, 3 halves quantity cubed minus 9. Okay, 3 halves quantity squared. Okay, plus 12 quantity 3 halves minus 3. So that we'll find the point of inflection. Okay. So this would be equal to, calculating that solution. So that would also give us another 3 halves. Okay. So that the point of inflection is located at 3 halves and 3 halves. Okay. So let's now try to graph that. Okay. So the graph would look something like this. I think I should erase everything here so that we can, or just approximate and minimize the graph. Okay. So we have 1 and 2. So say we have 2 points. So 1, 2. Okay. So then 1 and 2. Okay. So at x is equal to 1, the value of y is equals to 2. So here. If x is equals to 2, the value of y is equals to 1. Our point of inflection is located at 1.5 and 1.5, so 1 and 1 half, so that would be located here. And our graph would look something like this. So the graph would look something like this. We know that at 2 and 1, that is at minimum, okay? So therefore, it's look like this. And at 1 and 2, that is at maximum. And this is our point of inflection, which is 3 halves. 3 halves. This is at point 1 and 2. And this is at point 2 and 1. So that's how we solve that one. So you have any problems or questions with regards to this example? So if you have problems, you have questions, comment it out. Or don't hesitate to send me a private message to my Facebook or any of my video. Okay, for sample problem number 3, let's have here a real-life application. Okay. So a farmer has enough money to build only 200 meters of fence. What are the dimensions of the field he can enclose the maximum area? Okay, so how do we solve this one? Okay. So the first thing that we'll do is to create relations and form two equations. Okay. So we have here a total length of 200 meters to enclose the field. Okay. So the 200 meters that can enclose the field, okay, so suppose we have here a rectangular field, okay, of an unknown figure, okay. So, what would be the dimension for our x and y? Okay. Suppose the total length that can enclose this would be equal to 200 meters, which is the perimeter. Okay, So for the perimeter, we know that if you have x and y, the perimeter is simply equal to twice x plus twice y is equals to 200. Okay. So let's manipulate. We can factor out or we can introduce 1/2 to both sides. So 1/2 and 2x, so that will leave us with x. 2y and 1/2, that will leave us with y. And 200 times 1/2, that will leave us with 100. Let this be our first equation. For our second equation, we know that the area is simply equal to our x and y. Okay? We don't know the area, okay? The maximum area. So to find the maximum area, we'll need to find the derivative of this. But to find the derivative of this with respect to a single variable, we need to eliminate one variable using the first equation. So we're going to call this as equation number 2. So let's manipulate this. Suppose we want to remove y, okay? So that everything will be equated to x. So that y is equals to 100 minus x, okay? Which is also our first equation. Oops, sorry for that cut. So y is equals to 100 minus x, and that will be our first equation. Okay, so we can now substitute this equation with this equation so that we can equate area is equal to x quantity 100 minus x. And this will be our third equation based from 1 and 2. Okay? So right now, okay, so we're going to simplify this, okay, or rearrange this. So that area is equal to x quantity, okay, or rather x times, where is this? So that would be x times 100 minus x squared, okay, and that would be our area, or area is equal to 100x minus x squared. So that would be our third equation rearranged. Now, we'll find the derivative of everything, okay, with respect to x, okay, so that dA over dx would then be equal to derivative of 100x with respect to x, so that would be 100, minus derivative of x squared, so that would be 2x. Okay, now, we'll need to solve, so we're going to solve for the critical value, okay, and then we're going to equate that to 0. So that 0 is equal to 100 minus 2x. And that will be our equation now. So it doesn't matter if that will be the minimum or the maximum value since we'll determine that later. So transposing 2x to the other side, so we'll have 2x is equals to 100. So that x is equals to 50. And that will be our first dimension. So, we will use this value to find our y, substituting that here in number 1, so that 50 plus y is equals to 100, so that y is equals to 50. Okay. So that we'll have a dimension of 50 by 50, okay, which leads to a field that can be fenced by 200 meters of material, and that would be the answer. So that would be 50 by 50, or simply, a maximum figure that can be enclosed is a square. So do you have any problems or questions with regards to this example? So if you have problems, you have clarifications, comment it out. Don't hesitate to send me a private message to any of my videos.